course, want to extend my gratitude to the announcer for providing such a consistent welcome to all the speakers, including myself. Yeah, so I work at Sciton. We're a laser company. I think there's a lot of people in the audience that don't use lasers very much or aren't as familiar as typically the audiences that I would speak to are. So what we do is we make these medical devices. They're lasers. We're located in Silicon Valley, right next to San Francisco. And what our devices do is they shine light on skin, as you can see in this scientific illustration I have here. And so what you might want to do if you're shining light onto skin, the very first thing is you might want to remove some of that skin. So we call that ablation. You might want to even the skin tone. So that's what photothermolysis is for melanin. You may want to eliminate vascular issues, smooth skin texture, which is what you do when you do collagen remodeling. Or you might want to just kill bacteria, which would be like an acne treatment. This is just a simple list of what you may be trying to do when you shine light onto skin. But in my position at Sciton as an R&D person, I look at a lot of graphs and I look at a lot of science. And actually, if you've been to a laser conference before, you've probably seen a graph like this before. It's a graph of the absorption coefficient of light as it travels through different chromophores that are in your skin. The blue one is water, and then melanin and blood. And the thing that I don't like about this graph is that it's so scientific, and I can't imagine what I would tell somebody to distill from this graph when they're actually doing a treatment. Like, I don't think April here is going to look at that graph and be like, yes, the absorption coefficient is 10 inverse millimeters, so that means I have to increase the energy by 2 notches. So there's a kind of a big disconnect in between the idea of the science and the idea of actually doing a treatment. And I've spent the last 5 years of my life trying to sort of bridge this gap, and I've put a lot of thought into this. Now, the first thing I thought of is, why do people actually like showing this graph? I actually asked my boss, Dan Negus, the company founder, I said, Dan, why does everyone love this graph so much? It doesn't make sense to our clinicians, to our customers, really to anyone. And I thought about it in a non-rhetorical sense. I thought about why people actually liked it. And the reason that is kind of engaging is that just by shining light into water, you can actually see the effects of the actual water molecule. The water molecule looks like a little wishbone, with the hydrogen atoms on the bottom and the oxygen atom on the top. And so you can actually see the different ways that this thing vibrates and wiggles around right in this spectrum here from a very simple measurement. But of course, our clinicians probably don't care about this. They might think it's kind of neat, as I do, but they don't actually care about this when they're actually doing a treatment. So what I've been doing is I've been saying, well, let's not talk about absorption coefficient. Let's just talk about how far does the light travel through water and therefore your skin. So instead of talking about 3 inverse millimeters, I can say that it travels into your skin about 1/3 of a millimeter. And so if I zoom in on this graph, now it makes a lot more intuitive sense. So our laser, which we have outside, it will apply three different wavelengths all at once. One of them is 1470. That travels into your skin about 0.35 millimeters. One is 1927. That travels into your skin about 0.09 millimeters. And then, of course, 2940 just stays at the surface because it's ablative. And so you can actually see the direct effects of this. You can actually see, if you reframe the graph in this way, you can actually see how this actually affects our patients. And this is why the basic physics of that light actually affects the results that you get. But I can actually even go one step further. We were lucky enough to get a VivoSight OCT, and I can actually look at my skin after I do treatments with these 2 wavelengths, and you can actually see the difference. These are identical energy, same spot size, everything. You can see if I look a little bit into my epidermis that this 1927 wavelength is so much more shallow. It's really good for treating pigment, and so you can see it has effects on the epidermis, whereas 1470 is a lot deeper, so it doesn't. So we've really been trying to reframe all of how we communicate to our clinicians and to our providers and to our customers, not in terms of this raw basic science that they might not resonate well with, but more in terms of actual real results. And I'm just going to talk very briefly about that 3rd wavelength, which is the 2940 nanometer wavelength. Again, you've probably seen this graph before, and I've been saying why it's difficult to communicate to people in common audiences. One thing which I also didn't like about this graph, even though it shows you all of these nice molecular resonances of the water molecule, it's also on a log axis. And you don't really need to know what that means, except for the fact that if you actually look at it as normal people would actually look at a graph, it actually looks like the graph that I've put on the right. This is just a normal axis. You notice on the graph on the left, it doesn't go to 0 on either of them. On the one on the right, it does. That's because it's sort of presented normally. And this is why Sciton, and this is why my company, but the company that I work at, is so excited about the 2940 nanometer wavelength, and it really shows you why this is now, because we're presenting it in a way which is a little bit more intuitive. And probably the most intuitive way I can show it is just if I look with a thermal camera as I do a treatment down my arm with two different devices, one with our 2940 nanometer wavelength, and then another with the CO2 wavelength of about 10 microns. And so you can see, and we can actually show directly the people that use our devices the difference in the amount of heat deposited based on using 2940 for cold ablation or for using a CO2 device with cold ablation. So I just want to conclude by saying, and yeah, this is why the erbium doped YAG wavelength is so much better, and in fact, it shows better and better healing times and reduced complications. So just I want to conclude by saying that we can pick wavelengths based on the penetration depths that we want to treat, and then we can now look at this better when we reframe all of our actual scientific data into things that people actually care about and want to talk about. Except for ablation, of course, 2940 is better than everything. And the thing that I've sort of come to the conclusion is that our customers don't care about the scientific graphs that we show them. They really care more about their patients, and that's the thing that matters to them. And so, thank you.